Good afternoon and good morning, everyone. And thank you for joining me today. We're doing the webinar on rethinking outdoor air and how IAQP unlocks healthier and lower energy buildings. First, a little bit about myself. So my name is Luis Marquez. I'm a certified air filtration specialist. I'm a VP of engineering here at Blade Air. So today, I'll be covering why traditional ventilation design may overuse some of the outdoor air. I'll also specifically talk about ASHRAE's indoor air quality procedure and how that may be a better way to size your outdoor air coming in. And then we'll go over an example of both of ASHRAE's ventilation rate procedure and indoor air quality procedures that I use for introducing clean air to a given space. So before we continue, I am coming to you from Toronto, Ontario, Canada, and the land that we are meeting on is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis people. We also acknowledge that Toronto is covered by Treaty 13 with the Mississaugas of the Credit. On the agenda for today, we'll be covering some of the existing energy realities. I'll touch a little bit upon why ventilation and specifically minimum ventilation matters. And then I'll go quickly introducing the ventilation rate procedure and the indoor air quality procedure. That is what ASHRAE provides, along with a little bit of the case study, and we'll conclude with some takeaways and Q&A. So we'll start first with a question. What if you're wasting 60 to 80% of your HVAC budget annually? Now, this question isn't rhetorical. This is more of a reality that happens from overventilation of outdoor air. Traditional ventilation approaches often overcondition outdoor air by 60 to 80% beyond what's necessary for acceptable indoor air quality. Now, the reason this happens is mainly because it considers outdoor air as 100% clean, and these approaches aim to dilute any indoor air contaminants, essentially replacing as much of the indoor air with outdoor fresh air as possible. Now, the problem is that this outdoor air must be conditioned before being introduced into the space. This conditioning, which basically means, bringing it to room temperature and a proper humidity, is what really results in that 60 to 80% of energy increase than what is actually needed or in order to achieve clean air. So what does this overconditioning actually represent? As many of you may know, HVAC systems encompass about half of your total building energy. So when we're talking about this, it's really 25 to 40% of your total building energy budget that could be optimized. So we can recognize this both as a significant operational expense and actually our greatest opportunity for optimization. This is really crucial now more than ever. Utility rates are escalating to 4% annually, and we're looking that it's going to continue to increase with more adoption of AI and data centers, which are going to further strain the grid. Traditional ventilation approaches were basically developed when energy was relatively inexpensive and indoor air quality concerns were less sophisticated. I think today's technical standards and economic realities demand more intelligent approaches, and we need to optimize both energy consumption and air quality outcomes simultaneously, now more than ever. So let's first take a step back and understand why ventilation and minimum ventilation really matters. According to ASHRAE, ventilation is critical for providing acceptable indoor air quality, which protects occupants from adverse health effects. And it achieves this mainly by bringing in fresh air and diluting and removing the contaminants. The second aspect is comfort. So ventilation really helps to maintain, as I mentioned before, ambient temperature, ambient humidity that's actually comfortable for people, and odor control in many cases. So we really are looking at to, number one, maintain good health within the space, and number two, allow the people in the space to be comfortable. So not too cold, not too hot, not too wet and humid, or not too dry. For a long time, actually for many, many decades, ASHRAE has provided two methods for ensuring clean air in a space. The ventilation rate procedure, or VRP, and the indoor air quality procedure, or IAQP. Again, the problem arises in that the method of providing ventilation to achieve these goals never really considered energy as a major factor. So today we're gonna really examine how each method handles the approach of cleaning air, and why most HVAC designers generally look at the ventilation rate procedure without considering the IAQP method much, if at all. Let's start with the ventilation rate procedure. The ventilation rate procedure represents the traditional approach and the one that's most currently in use. And so it's a prescriptive method and a prescriptive approach that kind of creates an energy and efficiency. And from a technical standpoint, the fundamental flaw is that the VRP was developed as a prescriptive one-size-fits-all approach, and it's based primarily on CO2 control and general occupancy assumptions. It doesn't consider the actual contaminants that are inside the space, or the quality of the outdoor air source. So from a technical perspective, VRP essentially treats all outdoor air as perfectly clean dilution air. And so what that leads to is that it requires you to condition many times large volumes, regardless of whether that conditioning is actually necessary for air quality. This can become really, particularly problematic if you think about any urban or industrial environments where outdoor air may actually introduce more contaminants than it removes. And so it can also bring potential harmful gases and particulates to the indoor settings during events like wildfires. So, for example, this summer, we had some wildfires rolling in to Toronto, and I had my IAQ sensor, and I could see outside. Concentration rates were anywhere between 50 and 80 micrograms per meters cube. And I go into the hallway of my condominium, and it's even higher. And so essentially they're just bringing in that dirty outside air and actually just making it worse and concentrating it within the space. Using the ventilation rate procedure, it would tell you just bring in more air and you'll be fine. But really you would just be exacerbating the problem. And so additionally, there are energy consequences, which are quite significant. So you're operating heating and cooling systems to condition this outside air, and generally they use about 3 times more energy than just recirculating what is already conditioned air. And as I mentioned, in the worst case scenarios, you're actually degrading your indoor air quality by introducing polluted outdoor air. In the end, the mathematical result is that you're potentially overconditioning by that 60 to 80% beyond what's required for acceptable indoor air quality. And so this represents not just energy waste, but a fundamental engineering inefficiency that can be addressed by just being a little bit smarter and more performance-based. And so that brings us to the indoor air quality procedure, or the IAQP. So ASHRAE's indoor air quality procedure represents a shift from prescriptive to performance-based ventilation design. So instead of assuming outdoor air dilution as a primary strategy, IAQP really focuses on maintaining specific pollutant concentrations and keeping those below established limits through optimized source control and air cleaning. So the methodology considers specific contaminants that includes particulate matter, specifically PM 2.5, and common VOCs, and they establish concentration targets that are good for health and comfort. Now, the good thing is the IAQP does allow for any of these contaminants to be modified as needed. So you can include specific pollutants that are important to the specific space that you're trying to control. So this approach allows engineers to reduce outdoor air intake when effective air cleaning technologies can maintain the concentration limits through just recirculated air treatment. So I think one important thing to note is that despite it being available for several decades, it was often seen as quite complex. And thankfully, some recent updates to the most recent standard in 2022 have simplified the IQP implementation, and ASHRAE has actually provided some standard contaminant lists as well as concentration limits and calculation tools. The procedure now includes clear guidelines for air cleaning technologies, performance requirements, and integration with HVAC systems that, along with better filtration, should allow for more adoption of the procedure. And regarding the energy effects, essentially, when you're using advanced filtration technologies, whether that be filters or otherwise, that can clean the circulated air, and the outdoor air, that allows for cleaner preconditioned air to be used for real dilution and real reduction of the air inside and not using what is sometimes dirtier outside air. Let's kind of look at this from an example, which I find is a much better than the theory. So I'll set kind of the scene. And so for this theoretical study, I've chosen 5 classrooms, and each of these classrooms we'll assume has 1,000 square feet of area. And within each of these classrooms, let's say there's 25 total occupants. So that's the students and the teacher. And so this can create, a representative commercial application that's a little bit easier to understand. And I'm using nice round numbers. On the duct efficiency, this really just means that, how effective your existing HVAC is at bringing the outdoor air to your specific space. So I'm just going to assume 80%, which is a pretty standard and conservative number. But you can change that as necessary. As a supplier, I've chosen a standard RTU, and that I picked a Train 10-ton precedent unit, as those are pretty common RTUs that are used in educational and commercial applications. For our location, I decided to go with Newark, New Jersey, mostly because the information for outdoor air quality is readily available on the APA, and because it does give us a nice urban environment that is representative of many cities throughout North America. For the energy part, which I'll get to at the end, we'll assume that it's a nice hot and summer day with 95 degrees Fahrenheit or 25 degrees Celsius. And indoors, we would like it to be a more natural 75 degrees Fahrenheit or 24 degrees Celsius and 50% humidity. With that in mind, let's take a look at how each procedure would look at this problem. So for the VRP method, the calculation is really very simple. ASHRAE gives us kind of how many CFM per person is required for a classroom, and it actually gives us how many CFM per square foot. We can really just plug these in directly into that first equation that I have there, which is really saying, this is how many square feet I have, this is how many I need per square feet, this is how many people I have, this is how many CFM I need per person. And then dividing by our duct efficiency, we see that we get for each one of these theoretical classrooms, I would need 462.5 CFM. The other thing that ASHRAE considers in its VRP method is what's called multi-zone systems. And all that really says is that I have 5 classrooms and 1 RTU. So I'm really using several zones. And so ASHRAE recommends a 1.5 safety factor to be implemented. So with that in mind, I take my 462 CFM For each classroom, I multiply it by the 5 classrooms, my safety factor, and I get in total. The VRP method recommends that to maintain clean air, I should provide 3,500 CFM of outdoor air. The good news for me is that, I made up this example, and so my RTU is correctly sized. It provides 4,000 CFM, and so I can run, my train unit at 82% of its max rated value, which is good for me. Let's see how the IAQP method, takes the same problem. The key with the IAQP method is using air cleaning technology. So in my case, I'm going to use the Blade Air Pro filter. I'm going to put that into my system into the location B that you can see on the diagram on the bottom right. Putting it in this location allows it to clean both the outdoor air coming in and the recirculated air. Besides the cleaning technology, I'm going to consider my indoor generation levels, and ASHRAE provides that for classrooms. But you can also use actual measured levels if you have any type of measurements or IAQ tools in your site. Likewise, for outdoor air concentrations, ASHRAE provides, and you can use the EPA data that's available publicly, and that's just local stations that are in every major city or nearby airports, and they provide outdoor concentrations for many, many, many pollutants. So you can use those publicly available tools, or again, if you have your own measurements, it's perfectly fine and even sometimes more accurate to put those in where you can. Once I have that data, I use the IAQP calculator tool and the filtration capabilities of my air cleaner. Now, one thing to note is the IAQP still considers the area of the space and the effectiveness of the duct system. So I'll keep those the same at 80%. So you can see the diagram here of the multi-zone method. And so an iterative approach is taken, meaning those equations that you see at the top there actually get run many, many times within each other. And for each one of those rooms that are in the diagram, there's only 2, but it would do that for the 5 rooms. Now there's a nice Excel calculator that IAQP provides to be able to do this. Here's a little bit of a simpler diagram to better visualize what is being calculated. At each calculation, we are evaluating the concentrations in the conditioned space. We calculate the increasing contamination of the space, and that's represented by the plus side. And so this includes the supply air that's being brought in. So that means the outdoor air contamination, as well as the recirculated air concentration. And it also considers any point sources and any other pollutants that are being introduced within the space itself. On the minus side, we are considering our removal rate. So that includes air being exhausted out, air being treated either by filtration or any other air cleaning method at the recirculation stage, or really at any point within the system. And so all this essentially it's a mass balance equation to ensure acceptable indoor air quality. Here's really the results. So now that we understand kind of what is happening, I'll show you what the inputs and outputs of the numbers that are being inserted into the calculator. In the top right, you can see I've inputted our 5 classrooms, the same 3,500 CFM of supply air, and it's distributed between the 5 rooms, so 700 CFM. On the bottom left there, you see the outdoor concentration rates for each of I have the 15 standard pollutants there, and that is EPA outdoor data for my location in New York, New Jersey. And then I actually have the generation rates for a classroom that's also provided by ASHRAE. And again, I can include any other pollutants that I want or remove any pollutants that I want. And then I can also include here the measured concentration rates if I have those from my own sensor data. And so I insert these into the calculation and run the iterative process. And so I get what's out in the bottom right, and that gives you the actual concentration results for each one of those. I've also put there, how far away we are from actual limits, which is quite significant. So the IAQP calculator indeed confirms that if we supply the 3,500 CFM that the VRP called for, we would indeed have nice and clean air. Now, what it actually confirms is that my filtration ability is so good that I'm actually going to have cleaner air if I were to supply 100% recirculated air. Nobody would ever recommend 100% recirculated air for both CO2 reasons and just comfort. But we could go with outdoor ventilation. Good is 5 CFM per person. Multiply that by the 125 people in our 5 classrooms, and we essentially can get that we can meet very, very clean air by just bringing in 625 CFM of outdoor air, and the rest of it be recirculated. And so that's summarized in the top right, where you see the zone recirculated air and uncorrected IAQP outdoor air. And essentially what I've done is I've taken the same 3,500 CFM of outdoor supply air and redistributed as 625 CFM outdoor and 2,875 CFM recirculated, and still I'm ensuring that I have nice and clean air. I think the question you all must have at this point is, what does that outdoor air reduction actually mean from an energy perspective? And so to answer that, I'll take the stats and the data sheet from my train RTU. And I already mentioned kind of, we'll assume a really, really hot day and kind of what we want in our indoor standard air. So 24 degrees Celsius or 75 degrees Fahrenheit and 50% humidity. So using our thermal energy loss that in the first equation, and then calculating for the sensible and the latent heating shown in the second equation. And that just means that we're not just considering the temperature change, but also the humidity change. And so we can actually calculate how much more energy is required for us to condition that outside air, which adds up to 69.33 kilowatts of thermal powered. And thankfully, our data sheet has our efficiency of conversion. So that 69.3 thermal, using our EER number, tells us that our train unit would need 6.3 kilowatts of electrical power to be able to accomplish that. What we really have is that if you were in this school for 6 hours and you were trying to cool that air, you would save about 37.8 kilowatt hours of energy for that single day alone, just by using the recirculated air versus what the original VRP would say you need at least 3,500 CFM of outdoor air. While the ventilation rate procedure is a good rule of thumb and a good starting point necessary to ensure minimum ventilation rates and supply air sizing, the IAQP method can be used to better decide the ratio of recirculated air versus new air that needs to be conditioned into the space in order to really ensure optimal air quality and actually improve energy efficiency. Another thing to take away is that the IAQP is effective, really depending on your air cleaning technology or the filter that is being used. If you don't have good filtration, then it's not going to work at the end of the day. You're looking to reduce the concentration rates. And then obviously the sample I've given today was very idealized, but it can be used equally in other types of spaces and with different types of contaminants. And while it can be a little bit daunting at first, if applied correctly, it really can help your clients and your end users a lot of energy and money. It can really reduce outdoor air intake by as much as 60 to 80% by using this method.
Thank you, Luis. And as he said, if there are any questions, please feel free to put them in the Q&A section. We will stick on for a few minutes to see if any roll in. And if not, please feel free to follow up with us directly or your account representative. As far as airflow reduction in the example, what % was it reduced with your blade filter?
That's a good question. It's off the top of my head, but it was actually, I believe, 82 or 84%. So it's a little bit higher than just a couple of percentages higher than what I gave as 60 to 80%. It really depends on the existing system, and most spaces won't be bringing in 100% outdoor air, which I was doing in my example. And so from a realistic or existing, you're more likely to be in that 60 to 80% reduction range.
Are these different than dynamic filters, or are these the same thing?
In terms of technology, is very similar, and we apply the same principles. I don't like to talk about our competitors, but we do very similar things. We just do it better and more efficient. But technology wise, we apply the same principles.
With the IAQP, do you not have to measure the 15 pollutants continuously, or can you just do theoretical calculations like you just showed on your sheet based on assumed removal rates?
Yes. So the bare minimum would be to use the assumed, and these are the very much the recommended and things that you should consider in a space. If you take a look at the ones that have there for most spaces, the actual concentration rates of these pollutants are very low, which is why it actually brings the problem that most of the time we're over conditioning and bringing in too much outdoor air. In reality, you can apply this to kind of what you really need, including pollutants that aren't on there. So what I mean by that is you can use what you kind of have as actual concentration rates or what is shown to be studies or published data, or you can just use measurement of very specific contaminants you're trying to remove. At the end of the day, the goal is to have a minimum amount of clean air and ensure the comfort and health of the people inside. So in most general usages, those contaminants that are there are in very low concentrations, both in the indoor air and the outdoors. So it is really, for the most part, a very low risk when you actually do the math of putting those in.
Does ASHRAE 241 impact any of this?
That's a great question. So ASHRAE 241 is very much, one is it's meant for bioaerosols, which I didn't have any of in my example. So that's, viruses, bacterias, and any other of these types. And ASHRAE 241 was really developed for something like the COVID-19 pandemic. Essentially, what it says is you need to have a plan in the event that there is another pandemic or similar like event. And what the approach for that is you basically need to ensure minimum cleaning rates, even in the event of these increase. So what it'll say is assume that you have this increased concentration rates. What's your actual result and how many people can you still accommodate within these concentrations? And so in practicality, it's actually very similar to the IAQP and was necessary because nobody was using this kind of concentration. The nice thing about 241 is it allows you for other ways to quote unquote clean the air, which was necessary to be able to allow for, say, not everybody, staying in their homes, but instead saying, you know what, we can be in a classroom as long as you have cleaning air technologies like, say, a pro filter in your duct and then maybe an air purifier in the room. And so that's really the intent of ASHRAE 241.
We've had a request if the IAQP spreadsheet that you've been referring to from ASHRAE is available online.
It is. It's available online for a price. I forget what the actual price is. I'm going to say somewhere between 100 and 200 US dollars. And it provides both the ventilation rate procedure calculator and the IAQP calculator. It's 2 Excel sheets with a bunch of macros. And it does take some time to get used to, but it does really do the calculation itself. It really just does the calculations that were in those nice looking equations that I showed in one of those previous slides. I would say ASHRAE is not the clearest in terms of presenting the information, but if you're able to understand it, it is really useful. And when not, like, I would rely on the manufacturers and come with the distributors and the air specialists to kind of help you out through these. At the end of the day, a lot of my time spent as a certified air filtration specialist and just as Blade Air is helping out our clients and end users, and we're always open to helping to have those conversations because we understand for a lot of the end users it may not be so clear, especially when you're trying to go through the actual math, if you will.
Where does one obtain live local data of outdoor air concentration rates for Canada?
I use the EPA just because it's the more North America and it's the actual one that ASHRAE provides. Canada does provide public data as well. Actually, every airport has local data on air quality pollutants that are available to the public website. I don't have one the exact one off the top of my head, but we can certainly find that and send that out. But yes, it is publicly available to a lot of the pollutants, certainly the very common ones, PM 2.5, and some of the formaldehyde and such.
Luis, thank you again for today and a great presentation. Hope you all have a great rest of your day and see you soon.